Hey everyone, in geometry, it is Mr. Canfield. Today we're doing chapter 5, part 1, perpendicular bisectors and angle bisectors. So we're going to start out with a launch activity on Savas. If you missed it in class, that's okay. You're going to miss some fun discussion, but we're going to then move on to this. So this says, use your compass to find points that are equidistant or equidistant from both endpoints of this line segment. What do you notice? So if you remember, we've used a compass in here before. If I kind of open it up and as long as I open it up more than halfway and I put the point on one end and draw an arc above and below, I can do the same thing over here and I can draw the arc above and below. And if I do that, well, then I end up with 2 points. And these 2 points have to be equidistant because the way that I found them was I used this amount. It's this amount up here and down here. So it's that amount from that point, and it's the same amount from the other point. Oh, same amount from the other point. So I know that those are equidistant, and I could open it up to a different length. I could even open it up much wider and still, so now I wind up putting a crossing up there, and I can do the same thing over here, put a crossing up there. Oh, I forgot to go down here. So if I do the same thing, get super spaced out, I made 2 more points that, now they're not the same distance as these two are, but I can't even see it on the screen. But they are the same distance from these 2 points. So we could do this a few more times. I'll do it one more time for the video in class. I'm gonna give people a few minutes to mess around with this. Let's get kind of closer. Let's do like over here. So if I try that one, so, and again, all these points end up being equidistant. And so that leads us into what the heck this actually is. And that is all these points line up on what's called the perpendicular bisector of that line segment, right? It's perpendicular and it cuts it in half. So I don't know if you can see on my drawing, and maybe there's a little bit shorter on this side than on this side, but it's more from me using a marker and the way that I'm doing it. But what's supposed to happen is that that and that are in fact the same. So because of that, excuse me, it leads us into a new idea, a new theorem. And that new theorem is that anytime we're looking at a perpendicular bisector, any point on the perpendicular bisector, like if I pick that point makes can make 2 sides that have equal length. Why did I draw it to that? Guys, I'm tired. Oh my goodness. It was supposed to go to here. It's supposed to go to the endpoints. Looks so nice too. What it was supposed to be to here. And I can pick, so that and that have to be the same thing. And I could pick any point anywhere on this perpendicular bisector. Like if I pick that point down there, and I connect these, that point is equidistant to both endpoints of my perpendicular bisector. So it's a thing. All right, so let's move on and start doing some problems with it. Hope I didn't bleed through the paper too bad. All right, not too bad. So here's the theorem. And so we can say that if we've got a perpendicular bisector, then any point on the perpendicular bisector is going to be equidistant. So that's the theorem, but the reverse of that is also true, where if I have some point that's equidistant, which is kind of how we did the front. And you might kind of struggle to see how this is even different from what I'm talking about. So the theorem says if you have the perpendicular bisector, each point is equidistant to those two. The reverse, or what we call the converse, is pick a point that's equidistant from these two guys, and it has to end up on the perpendicular bisector. So that's like saying if we don't already have the perpendicular bisector, but we know a point is equidistant to the two of them, then we know it's on that perpendicular bisector, even if we don't know what it is yet. So that's our theorem. Now let's do some problems. So problem number not labeled. Number 1. So we have this here. You see the right triangle. Honestly, this is the kind of thing where I look at this and I would go, like, even without knowing the theorems that we know, well, like, it looks like we got two like equal things. So I can say 6x minus 10 equals 3x plus 2. Now, I know this is true because 11, 11, make a wish. We see that it's the same amount on both sides of this and it's perpendicular. So we have the perpendicular bisector and this point is on the perpendicular bisector. So I know that these two are equal to each other. But you probably can see that they have to be the same even without necessarily knowing that theorem. So solving this, lots of different ways to solve it. And we're solving a lot of equations like this today. So I'm going to solve this the standard way first, and then I'll do other ways for different ones. So the standard way, we have x on both sides. Let's take the x that's on the right-hand side and subtract it from both sides of the equation. Now, I gloss over this a lot. On the left side, this is the right side. On the right side, 3x minus 3x cancels. What's left over here? Plus 2. So just a 2 is left over. On the left-hand side, well, and notice we did minus 3x from the 3x. The 2 doesn't get affected at all. It's just the 3x that gets affected. And over here, I have to subtract 3x from the thing that is the same kind of term. So you can't go up to somebody with 8 apples and say, hey, give me 3 of your oranges. They'll be like, what? If the x's are like apples and the numbers are like oranges, we got to take apples away from apples and apples away from apples. We can't take apples away from oranges. They don't say, hey, give me 3 of your x's, and 10's like, I don't have any x's. I can't do that. So here, 6x take away 3x, we're left with 3x, and then we have a minus 10 left over, so we bring that down. So in our next step, we're trying to get x by itself, so I got the 3 and the 10. I'm gonna get rid of the 10 first. We always, when we're trying to isolate x, adding and subtracting is easiest to do first. We do all the adding and subtracting until there's none left to do, and then we'll do division. So I'm going to add the 10 to both sides. 3x is equal to 10 plus 2 is 12. We'll divide both sides by 3, and we get x is equal to 4. So it says, what's the measure of AD, though? So solve for x, I got x is equal to 4. So if I want to know what AD is, well, it looks like it's longer than, wait, don't worry about what it looks like. Focus on 3x plus 2. Well, I know x is 4. So I know AD is 3x plus 2. I can do 3x plus 2, but instead of writing x, I can substitute 4 in. So 3 times 4 is 12, plus 2, so 14. And you can do the same thing over here, and it should get you 14 as well, even though it's not asking me for that, because of what we know about this situation. All right. What is the value of a WY? Well, gee, look at this. I got a perpendicular thingy. Maybe it's a bisector. Oh, it definitely is, because that and that are the same. And so the way this theorem works is, since those are the same, and we got perpendicular here, we're guaranteed then that this and this are also the same. So I can say 5n minus 2 is equal to 2n plus 7. So here's another way to solve an equation like this. I want to move the 2 over here. I know eventually I'm going to move that negative 2 and move it over to the other side. So I'm going to do them both at the same time. I'm going to subtract 2n from here and from the 5n over here. And I'm also going to add 2 at the same time. So when I do that, that cancels, that cancels. 5 minus 2 is 3n. 7 plus 2 is 9. Now I'll just divide by 3 and get n is equal to 3. All right, so that's usually how I'll do these. And a lot of times I'll kind of do that step in my head. Like I'll just move this over and go, okay, I'm losing 2, I'll lose 2 here. I'm gaining 2, I'll gain 2 here, and then divide. All right. Oh, but it asks for WY. So to find WY, 2n plus 7, plug in the 3, right? I just took 2n plus 7 and I plugged in the 3. 2 times 3 is 6, plus 7 is 13. All right. So trying to keep this video as brief as I can, but still kind of cover all the ideas. All right, what's the value of OL? Okay, so I'm looking for this piece right here. And I look at this and my brain locks up because there's so much going on. So let me just kind of do what I can to get there. Okay, well, I noticed that this red piece here and this piece here have to be the same because I have a perpendicular bisector of this. Oh, I'm like done. Yep, okay, I got it. There's a lot of extra information in this problem, and it's way easier than it might seem at first. So I'm going to zoom in just on, so here's n, okay? This is 14. So I'm just focusing here. So I see this right angle here. These guys tell me it's a perpendicular bisector. So this is 14, that means this is 14. And then down here we have another perpendicular bisector, which I'll use a different color just to emphasize. So that means that this and this have to be the same, and it's a bisector, which means cut in half, so half of 14 is 7. So this has to be 7. So a lot of seemingly extra information, but that is just to show us that we have a bunch of perpendicular bisectors. Everything is actually cut in half, and we're good. If this had been like 17 and 15 or 17 and a different number, then we wouldn't be able to actually finish this problem like that. We'd have to do something else. All right, so next we're gonna watch a baggage inspector video. It is worth watching if you have access to like the virtual textbook in Savas. It's in 5-1. But basically what it does is it has this guy looking at a conveyor belt, and he has to like inspect the bags. So he's like, well, I want to stay like the same distance from each conveyor belt, and it's a conveyor belt that kind of splits like this. And so he goes through and he eventually finds out, oh, if I stand on the angle bisector, I'm always equidistant from both of these sides. And so that is the angle bisector theorem, that if a point is on the angle bisector, then it is equidistant from the two sides of the angle. So what that means for our diagram here is if we have this situation, that and that are the same. If we split the angle perfectly, then anywhere we pick makes it the same. So, you know, you just, that's actually pretty good. So if this is an angle bisector here, any point makes these, as long as it makes a right angle here. So those two would be the same. If I pick this point up here, then that would be, it's a different distance than that, but it'd be the same distance to this over here. So that's angle bisector and the idea of, or like how angle bisectors work. So using that idea, we have something like this. And again, you probably didn't need to know that to do a problem like this. It says find KL, and you'd be like, well, then those are probably supposed to be the same. So it'd be like 2x plus 3 is equal to 4x minus 11. So if you're gonna do the method that I've been suggesting on this, you're gonna subtract 4x from both sides. But when you do that, there's gonna be a little bit of a problem. I think I just said there's gonna be a little problem. There's gonna be a little problem besides camera shaking. And that problem is when I subtract 4x from both sides, 4 is bigger than 2. And when I subtract them, I'm gonna get a negative number over here. I personally don't like to deal with that. So what I do is, instead of moving the 4x over here, I'm actually going to subtract 2x from both sides. And when I do that, where's the x going to be? Well, it's going to be gone here, and it's going to end up over here. So we're going to have a 2x left over here. And I'll have a minus 11, so I'll add the 11 to both sides. 3 plus 11 is 14. So now I get 14 is equal to 2x if I divide both sides by 2. X is now by itself, so x is equal to 7. But that is still, it's another way we could do a problem like this. All right. Oh, and it wants me to find KL. So KL is 2x plus 3. So 2x plus 3. So 2 times 7 plus 3. That's 14 plus 3, which is 17. All right. On our next one, it says, if the measurement of angle BAD is 5x minus 7. So BAD is 5x minus 7. And you know, on tests and quizzes, I will normally give you these measurements. I won't have you have to read them like this. CAD is 2x plus 5. Let me look. Is this actually an angle bisector? Are these equal to each other? Well, as you see, we have this line segment. There's this point D, or sorry, this ray. This point D, and these line segments are equal to each other, and they're right angles. So we're guaranteed that it's an angle bisector. All right, so cool. It says, what's the measurement of BAC? So what is this whole angle here? Well, we'll get there. We can say 5x minus 7 is equal to 2x plus 5, right? They have to be equal to each other. Okay, so then I'll add the 7 to both sides, and I'll subtract the 2x from both sides. And I'll get 7x is equal to 12. Oh, wait, 5 minus 2 is 3, Canfield. 3. 5 minus 2, not 5 plus 2. So 5 minus 2 is 3. I'll divide both sides by 3. And I'll get x is equal to 4. And it wants to know what's the measurement of this whole angle here. So what I'll do is I can either find one of them and double it, or add them together and plug it in. It doesn't matter, it's the same. So if I do 5x minus 7, so 5 times 4 minus 7, I get 20 minus 7, I get 13. I should get 13 for both, because that's what's supposed to happen. So it's 26 total. Right, because 2 times 4 plus 5 is 8 plus 5, which is 13. So wow, it's like you add them together and you get 26. So yeah, several ways you can do it. That's one. All right, and we're already at the end of the lesson. So this part is for homework, and let's go through the lesson quiz. If you have not already tried the lesson quiz, wait, why would you? So go try the lesson quiz, like pause the video, spend a few minutes and go through and do them all. I'm gonna go over them, but I want you to have tried them first just to see what you know and what you don't know. Did you pause? All right, I'm gonna move on in 3, 2, 1. Okay, so CF is equal to 5. CD is equal to 12. EF is equal to 5. Okay, we got a perpendicular bisector. These are equal to each other. 5, 5 means 12, 12. What's the perimeter of CDE? CDE. Oh, so we got 12, 12, and 10. So 20, 12, 12, 10, 4, 34. All right. Number 2. What's the value of FC? All right. Oh, so this is like kind of what we did in our notes too, right? Where I see we got this, so we know that these two guys are equal to each other. So this whole thing here is 12. And then I got another little perpendicular bisector thing going on here. So this is 6 and 6. So FC would be 6. All right. Number 3. Which statement about the figure must be true? Select all that apply. All right. So before I look at this, I'm just going to look over here. What do I know? I know that PS is equal to PS, but that might not. Oh, they all have numbers. Okay, so it's going to be number based only. Oh, okay, so they need me to figure out. Well, I see these are equal, so that means that these have to be equal down here. So 6n plus 3 is equal to 4n plus 11. I'll subtract the 4 from both sides and get 2n. I'll subtract the 3 from both sides and get 8. And I'll divide both sides by 2 and get n is equal to 4. Okay, so n is not 4. And then 6 times 4 plus 3 is 24 plus 3, which is 27. So SR has to be 27 as well. And QR would be 27 and 27 together, which is 54. So no, no, yes, yes. All right, number 4, XWY is 20, and XWZ is 40. So it says this part's 20. The whole thing is 40. Well, that means this is 20 then too, right? XY is 16. What about what's YZ then? Well, so everything has to be equal then. So the trick was they didn't tell us this was 20, but they told us the whole thing was 40, so that's how we know that's 20. So then this has to be 16 as well. It is important that you're kind of able to back yourself up and go, okay, I know this is true, so this means this has to be true. Because if we can't do that, then like we could just kind of say anything and just, I guess it's true, it's fine. But then we might be wrong and not realize it. All right, which descriptions of the figure must be true? So it looks like we're going to solve again for x. I don't know that these two are equal. I'm assuming they're going to be equal, but I got to prove it to myself. So, oh, you know what? I see this side length here. I see angle, angle, side congruency. So that tells me that these two do have to be the same. So if I do that, then I can say that 7x minus 4 is equal to 5x plus 12. And the reason that I did that, I never want to do a problem and miss something silly. Like, just there's so many little details that could have gone wrong that it's just better to know that that they definitely have to be congruent. So let's see, I'll subtract the 5x from both sides, get 2x, I'll add the 4 to both sides, get 16. X is equal to 8. Okay, so A is true. KN, so 8, that's 56, that's 52. So KN is not 24. MN should be congruent, right? So that should be 52 as well. KL is equal to ML. So since I already found out these have to be congruent triangles, I know that those two have to be congruent as well. And then LN and LM are the same. That I am not guaranteed of, and it doesn't even look like it. So I got those for that one. All right, well, I hope this video was helpful. The homework is to do the 5-1 additional practice at the back of the packet. And if you're doing this on Schoology, you are always welcome to, like if you missed class and this is how you're catching up with this, you're always welcome to come in and get copies of this stuff so you don't have to print it out yourself or use your computer at home to do it. So hope it was helpful. Bye.